Hello, this is Bob Lessick at Johns Hopkins. This lecture is on the PAM matrix, the log odds table, and how it's used to score matches and mismatches, and how it's generated using matrix algebra. Looking at our objectives, be familiar with what a substitution matrix is and what it's used for. The PAM1 is the basis of all the other PAM matrices, and it's generated using a log odds table. Explain how matrix algebra is used, because matrix multiplication can be used to generate longer PAM. And then we'll score a very short alignment using PAM matrices. There will be a little exercise we'll do at the end. I'm going to be talking about matrix algebra, and if that sounds foreign to you, that's okay. Focus on the concept and the product. The product is a matrix that determines how to score each amino acid match or mismatch. PAM1 matrix was generated by Margaret Dayhoff, who collected related proteins and their structures. The term PAM actually comes from accepted point mutation, or APM, but PAM is easier to say than APM. The idea is to use the mutation rate in very closely related proteins. They actually analyze changes in protein families and which changes are accepted in nature. Presumably, they maintain function. One PAM is defined as a unit of distance of evolutionary divergence, in which 1% of the total amino acids have changed. Now to do that, you've got to use very, very closely related proteins. And she used protein families with greater than 85% identity. Very different from the BLOSSOM approach that we'll also see. So in an example, we'll use just one of the 20 amino acids. So starting with phenylalanine, at the distance at which 1% of the amino acids are changed, look at the left column. That's the PAM1 column. You see that phenylalanine is probably still phenylalanine because only 1% of amino acids have changed. So roughly 99% of the time, phenylalanine is still phenylalanine. Now, why is it not exactly 99%? Because PAM1 is 1% change for all 20 amino acids. So some are greater than 99% and some are less than 99%. It averages to 99%. Now, PAM250 on the right extrapolates that 1% change over a distance of 250 times. Now, you can't have 250% change, but you can mathematically extrapolate and show that after 250 units of evolutionary change, phenylalanine remains phenylalanine only about 32% of the time. But still, it's the predominant one of all the other amino acids. But note that some have a higher frequency than others. Now, we do that for all 20 amino acids. Here's what we have, a 20 by 20 table or matrix. And if you look along the main diagonal, you see that's where the 98 and 99% numbers are. Those are the exact matches. For instance, asparagine and asparagine, N and N. After 1% change, asparagine is probably asparagine 98.22% of the time. That's one that changes more frequently. So after we construct the PAM1 matrix, the idea is to extrapolate that 1% change over longer distances of time. And we can use matrix multiplication to do that. So the idea is that long-term changes of amino acids are based on short-term changes. It is an assumption. So we multiply the PAM1 matrix by itself. PAM1 times PAM1 equals PAM2. And that's a mathematical estimate of 2 units of evolutionary distance. Now, if we do that 250 times, that's 250 units of evolutionary change. Now, obviously, we can't do that because we can't measure 250% change, but we can do 1% change and extrapolate that to 250 units. So looking at this matrix, histidine is likely histidine 15% of the time. Some amino acids are even higher. Cysteine is important to protein structure because of disulfide bridges. So cysteine rarely changes in protein families because changes to cysteine are usually drastic. So it's 52% of the time that it's still cysteine. To put it another way, nature is somewhat intolerant to cysteine mutations. Let's look at arginine. Arginine is at 17% for remaining arginine, but actually 18% for lysine. Those are both positively charged amino acids, so it's not surprising that arginine could wind up as lysine. And just to point out, there's a mistake in the bottom corner. That 72 was obviously not correct because in the tryptophan column you've got a 55 and a 72. It actually should be a 7 followed by a 2 followed by a 4. Yeah, not that we're going to use this matrix. We use a log odds matrix for scoring, but I just want to point that out. So what we do is we take those percentages and then we take the log of the observed over the expected frequencies. And if the observed frequency is higher than the expected frequency, the log will be positive. If the observed frequency is lower than the expected frequency, the log odds will be negative. And if the observed equals the expected, it will be 0. The log of 1 is 0. And if we generate these numbers, we see histidine scores a positive 6. Cysteine, remember, had that high percentage. It scores a positive 12. So some matches actually score better than others. Now there's the arginine, R, and lysine, K. Remaining arginine scores higher. Now remember, it was 17% and lysine was 18%. So you might wonder, why is it a 6 for arginine and a 3 for lysine? Part of that is that lysine's expected frequency is higher. It's a more common amino acid. Remember, it's observed frequency over expected frequency for that particular amino acid. Also, the R to K mismatch still scores high. Nature tolerates arginine to lysine mismatches because both are positively charged. So that was the PAM 250 log odds matrix. That's what we use to score matches and mismatches. This is the PAM 10 log odds matrix. The thing you may notice is that there are really high numbers for matches and mismatches. Double digits for both positive and negative numbers. So this is a shallow matrix, which is useful for sequences that are close on the evolutionary scale. Whereas the high number PAM matrices are better for more distant relatives. And because these numbers are so high between the positive and negative, it's also good for short sequences that are too short to generate good statistics. Sometimes shallow matrices are used for that purpose. That was a lot of information, but to summarize, PAM1 is based on the mutation rate, the actual mutation rate. And then matrices like PAM10 and PAM250 are based on algebraic extrapolation. That's done by matrix algebra or matrix multiplication. So here's a quick exercise. Score this alignment using both the PAM10 and the PAM250 log odds matrix. Write down these sequences and use those matrices to score the matches and mismatches. And then add them up and use the discussion forum to discuss your results. Good luck.